We now know how to work with two different coordinate systems, Cartesian coordinates and polar coordinates. Now we'll add a third, and this will be the last set of unit vectors we work with in this course. These are normal tangential components, and they work like this. The tangential unit vector is called ut. Like velocity, it always points in the direction of motion. The normal unit vector is called un. It points normal to the path of motion and toward the center of curvature of the path, shown here as c. The third component is the binormal unit vector, ub. This is normal to the plane defined by ut and un, such that ub equals ut cross un. So in the picture shown, ub is coming out of the screen. Typically, there's no motion and thus no velocity or acceleration in the binormal direction. Normal tangential components are a bit unusual in that they have no coordinates, only the unit vectors that form a basis. However, they do have relevant magnitudes. In particular, rho is the distance from the center of curvature of the path of motion to the object of interest. Typically, the position of p with respect to e is not equal to negative rho un. When the path of motion is not circular, and hence the radius of curvature is changing, then at any given point, x and y, rho can be computed according to the equation shown. It's not as bad as it looks, it's just derivatives of y with respect to x. As with polar coordinates, normal tangential components also have standard equations for velocity and acceleration. Because the derivation of these equations for normal tangential components is less straightforward than for polar coordinates, I'm just going to give you the equations in this case. Here, the velocity of a point P with respect to inertial reference frame E is VUT because UT and velocity are both always tangent to the path of motion. And the acceleration of a point P with respect to E has a tangential component, AT, which is equal to V dot, and a component in the normal direction, AN, which is equal to V squared over rho. And again, rho is the radius of curvature of the path of motion. As with polar coordinates, these equations give you the velocity and acceleration of a particle as seen from an inertial reference frame, not as seen from the normal tangential reference frame. Also, along the tangential direction of motion, the three basic kinematic equations apply, as do the kinematic equations for constant acceleration. So you can think of curvilinear motion with normal tangential components as rectilinear motion along a curved path. We will definitely do some examples with NT components, but let's spend some time thinking about how they work first. The normal tangential unit vectors are said to be fixed in the path of motion and they move with the object of interest. As with polar coordinates, the motion of the unit vectors is a bit difficult to visualize, so here's an animation. The tangential unit vector, shown here as ET, always points in the direction of motion. The normal unit vector, shown as EN, always points toward the center of curvature of the path of motion and can change abruptly, as it does at the crossover point of this figure 8. Note that the binormal unit vector is always equal to ET cross EN, so it's coming out of the screen when the particle is on the right side of the figure 8 and going into the screen when the particle is on the left side, even though it's not shown here. Also, don't let the letter E for the unit vectors confuse you. The author of this animation simply uses a different notation convention. Now let's look at an example. A boat is traveling along a circular path having a radius of 100 feet. If its speed at t equals 0 is 15 feet per second and is increasing at 0.8 t feet per second squared, we're asked to determine its acceleration as viewed from an Earth-fixed reference frame at the instant t equals 5 seconds. One thing you need to be aware of with problems like this is that, as I've said before, velocity is always tangent to the path of motion. Moreover, when you're given v dot, it refers to the acceleration or change in speed along the path of motion. Recall that we said the acceleration vector is rarely tangent to the path of motion, so there's also likely to be a component of acceleration in the normal direction as well. As always, start by adding an Earth-fixed reference frame. Keep in mind that the center of curvature will frequently be moving, and it's not a good idea to fix an inertial reference frame in a point that is moving. However, since the path of motion is circular in this case, the center of curvature will be fixed, so we can set up the inertial reference frame with the origin at the center of curvature. Since we have information about a radius of curvature and velocity rather than x and y or r and theta, we can use normal tangential components here. So add the tangential unit vector and add the normal unit vector. We're asked for acceleration, so let's use the acceleration equation associated with normal tangential components. We were told that v dot is 0.8 t, and that is the tangential acceleration. We will need that again, but I'm going to set it aside for now so we can work on the normal component of acceleration. This is given by v squared over rho, so we'll need to find the magnitude of the velocity. Recall that along the tangential direction of motion, the basic kinematic equations apply. So here we'll use kinematic equation 2 in the tangential direction. And then rearrange. And now we can integrate, remembering that the initial speed is 15 feet per second. Now that we have an expression for the magnitude of the velocity in terms of time, we can reassemble the expression for acceleration. And now we just plug in t equals 5 seconds, remembering that the units of time do not contribute to the units of velocity or acceleration in this case. Do the computation and we find the acceleration of the boat with respect to our inertial reference frame is 4 ut plus 6.25 un, and that is in feet per second squared. We were given the acceleration in the tangential direction in the problem statement, but what is the acceleration in the normal direction? Well, this is called centripetal acceleration. It is the acceleration required to keep the boat on the curved path. Otherwise, it would continue on a rectilinear path. Let me explain a bit more completely. Say you have a ball on a string and you swing it around without hitting anyone, of course. What do you feel? What do you have to do to keep the ball from flying away from you? Well, you have to pull on the string to keep the ball from flying off in a straight path. You often hear people talk about centripetal and centrifugal forces. However, we can also refer to centripetal and centrifugal accelerations. Centrifugal acceleration or force, shown here in red, is fictitious. It feels real, but that's just because you're exerting an equal and opposite centripetal acceleration to keep the ball from flying away when you swing it. This centripetal acceleration, shown in blue, is the acceleration we're referring to when we talk about normal acceleration in a normal and tangential reference frame. Let's do one more example. A particle travels from point A to point B along a path consisting of two semicircles as shown. Each has a radius of 1 meter. If the particle's initial speed is 0 meters per second and increases at 1 meter per second squared, how long does it take the particle to travel from point A to point B? And what is its acceleration at point B as viewed from an Earth-fixed reference frame? To solve this problem, start by adding an Earth-fixed Cartesian reference frame at point E, which I will co-locate with point A. Then add normal tangential components fixed in the path of motion. Note also that the direction of UN will always point toward the center of curvature of the path of motion, so it will transition at point P from pointing toward the center of the semicircle on the left to pointing toward the center of the semicircle on the right. To find time, we can use the kinematic equations for constant acceleration. Because the particle is traveling along a semicircular path, we can figure out the distance traveled. And I'm going to call this S, or the distance traveled along the curvilinear path. Here, the distance traveled is 2 times the circumference of a semicircle, which is pi times the diameter divided by 2. So this becomes 2 pi rho, where rho is the radius of curvature. Given that we have the distance traveled, the initial velocity, and the acceleration, and we need the elapsed time, we can use equation 5s. Recall that this equation applies to motion along a curvilinear path, and even though it's not written in terms of vectors, We need to be careful to specify the direction of motion, which is ut in this case. Now I will rewrite that equation and use subscripts a and b to represent the beginning and ending points of the path of motion. If you prefer to use subscripts 0 and 1 to represent the initial and final time steps, that will work as well. Then I will plug in values, rearrange, and find that time is 3.54 seconds. To find the acceleration at point B, start with the appropriate normal tangential equation. We know that AT equals V dot equals 1 meter per second squared. This was given. We also know that AN equals V squared over rho, or more specifically, VB squared over rho, since we're interested in the acceleration at point B. We know rho, and we can compute velocity from the kinematic equations for constant acceleration. We know the initial speed, tangential acceleration, and now time. So use kinematic equation 4, noting that we're working in the ut direction only. And then just plug in values for the initial speed, tangential acceleration, and time. And we find that velocity is 3.54 meters per second in the tangential direction. Now we can return to the acceleration equation, which becomes 1 meter per second squared in the ut direction plus the velocity squared over rho, which is 12.6 meters per second squared in the un direction. I want to briefly review what we know about vectors now. Make sure that when you write a vector, the symbol has an arrow over it, and the right side of the equation includes both coordinates or scalars and unit vectors, which specify the direction for each scalar. Also make sure to include units as appropriate with the vectors. Since we now have the ability to work with not only Cartesian coordinates, but also polar coordinates and normal tangential components, using precise notation is more important. Remember that polar and normal tangential reference frames work only with curvilinear motion, so if a problem statement describes rectilinear motion, Cartesian coordinates might be the best choice. But if a problem statement describes curvilinear motion and includes the scalar coordinates r and theta, use polar coordinates. And if it provides a velocity only, try normal tangential components. There are exceptions to every rule, so you'll have to make a decision on a case by case basis, but this is a good rule of thumb to start with.